All right. Well, time for some more of you watching me talk about physics. So, yeah. This lecture is going to be about gases, mainly gases, and then we'll touch on plasma and plasmas at the end. Yeah. So we've already talked about solids and liquids, and how all these things are just made up of atoms, and atoms in different sort of varying forms of freedom, and whereas solids are pretty confined to the sort of structure that they're in. The atoms jiggle around, but they're stuck in that sort of structure. Liquids, the atoms are much more free to move around each other, but they're still sort of confined to the volume of the liquid. So a little bit more freedom of movement. And finally, gases is essentially the state where the atoms are just entirely free to move around, or almost nearly entirely free to just move around. And there's no real sense, unless you have some gas in a container, that a gas is going to be just like stay in its own sort of state together. Gas will just go wherever. Right. So, a couple things about gas and gases in general. Gases are free to move around, and they just fill up whatever space they're in. And unlike solids and liquids, which are both basically incompressible, gas and gases are compressible. So if you have a container of gas, then you can generally squeeze it down, at least to a large extent. An example of this, well, when I was saying in liquids, if you imagine taking a full water bottle and capping it off, fill to the brim, cap it off, and try to squeeze it, you're going to have a very hard time getting any more than a little tiny bit of movement. So that's that nearly incompressible nature of the liquid. Whereas with gases, you take a bottle, but it's empty it out. When you empty it out, there's actually just air in that bottle. So you close off the cap, there's air in there, so there's gas in there, and you could actually squeeze it down quite a bit. Right? At some point, it's going to get, you're going to squeeze it down so much that, as we'll talk about later, the pressure in the gas increases and it becomes very hard to squeeze it anymore. Right? But for a large degree, you can compress the gas down. So some just examples of gases. Very common form of gas is steam, gaseous H2O. And this is exhaust, could also be water vapor, might be some other kind of gas, but clouds are a form of gas generally too. And then finally, just our sort of diagram of a gas is all of these atoms. Again, atoms are what make up matter, and gas is just a form of matter, or form that matter can take. And in gases, all of the gases, the atoms that make up the gas, are just freely flying around in all sorts of directions. And also, as indicated by the little arrows, those arrows are sort of meant to indicate the velocity of each of those gases. And recalling that velocity is a vector, and the length of those arrows indicates the speed of the atom, or each of those individual atoms, right? The velocity for all of those is, pointing in all kinds of directions. It's also varying in speed, or how fast they're actually moving in those directions. So some of them moving slowly, some of them moving very quickly, most of them probably somewhere in the middle, sort of an average speed. And that will come back later when we talk about temperature. Okay. So, as I mentioned already, the air that we're breathing, and it's all around us, is a gas, and it's the most common form of gas that we experience. It is made up mostly of nitrogen, dinitrogen, N2, so a molecule of nitrogen, and oxygen, O2, molecule of oxygen. So it's a mixture of those gases, most of those gases. There's other trace gases too in there, but for the most part it's nitrogen and oxygen. So what is the properties, what sort of properties does air have? So, we started out talking about solids and talking about the density of solids, and then talked about liquids, and we talked mostly about pressure in terms of liquids, but I mentioned also that, density is also a property that liquid will have, just the mass of whatever liquid and divided by the volume of that liquid, that's the density of the liquid. So similarly for air has a density as well, and all gases are going to have a density too, and again it's the same concept. You just take the total mass of the gas that you have, divide it by the volume that gas is taking up, and there you go, you got the density of the gas. So if you recall, the density of water, or liquid H2O, is 1 gram per cubic centimeter, right? So in a cubic centimeter like this, almost like the size of a die, it's about a gram. And gram, I don't know, in terms of English measurements or standard measurements, I think a gram is maybe like a couple of teaspoons. I don't know. Standard measurements are so weird. Anyway, if you can imagine a small little cube of water, you could probably imagine about how much it weighs. It's a gram. That's what we call a gram. In terms of air, though, if you have a little like dice almost sized cube of air, but it's a little bit smaller than a die, so it would be a cubic centimeter. The density of air is about 0.001 grams per cubic centimeter, or 1,000th of a gram per cubic centimeter, which also actually translates to, if you had a cubic meter, so a meter is about 3 feet, so a cubic meter, if you had a cubic meter of air is going to be approximately 1 kilogram of mass. And a kilogram roughly translates to, I think, about 2 pounds. It's standard measurements are weird. But yeah, you could say that in a cubic, or roughly a cubic yard of air, there's about 2 pounds worth of matter there, nitrogen and oxygen mostly. So just comparing those two, water is about 1,000 times denser than air. And while the weight of air is small, it's not negligible. It's not something you just entirely ignore. For example, the weight of the air in an average room is roughly comparable to your own weight, right? Because maybe not quite like a bedroom, but maybe more like a sort of a lecture room or a conference room or things like that. So the volume of that room is maybe about roughly 1,000 times the volume of you. And since you are mostly made up of water, your density is roughly the same as water. So being 1,000 times bigger in volume than you, the room, the weight of the room in the air is roughly equal to the weight of yourself. So it's not nothing. It's certainly something. And we're going to dive more into what that means, that air does have that. So, the fact that we live in this environment that has air, it has nitrogen, it has oxygen, and it's a gas, it's all around us. We essentially, we call that gas that pervades around the surface of the Earth, we call that our atmosphere, right? And like I mentioned at the end of the last lecture, gases are very similar to liquids in that they both act as fluids. They both flow. They both can move freely in a very general sense. So, in that sort of analogy, or that metaphor in a way, we live, when we're on the surface of the Earth, we're living in essentially the bottom of an ocean of fluid. And that that fluid is the air, the gas that makes up the air, and the ocean is what we call our atmosphere. So combine all that together, all that air is what we call our atmosphere. So just like then when we talked about the pressure in a liquid, the pressure gets greater and greater as you get deeper and deeper into the liquid. The same thing applies for gases. As you drop deeper and deeper into a gas, the pressure is going to get greater and greater, and that pressure, in the same way as the pressure in a liquid, is due to the weight of the liquid above it. The pressure in the gas is the same. It's due to the weight of the gas that's above you. Right? It's all that gas pressing down, and in the end, that amounts to a pressure that pushes in all directions. And so another way of saying that is, since we live at essentially the bottom of this ocean of air, we're at sea level here. There are places that are maybe even deeper below sea level, but sea level for the most part would say is the deepest in the atmosphere we can go. So that's going to be the place where we're at the greatest pressure, right? We're the deepest in this ocean that we can go, in this fluid of air that we can go. And what that means is that if you go up in this fluid, if you get into higher and higher altitudes, you're getting less and less pressure. You're getting to a place with less and less pressure because there's less and less gas that makes up the atmosphere that is above you to cause that pressure. So it turns out that most of the atmosphere is within about the first 10 kilometers, or about 6 miles from the Earth's surface. So if we look at this image here, we see that going from sea level, this first sort of layer is what we call the troposphere, and that's up to about 10 kilometers, and it's probably something, I don't know, it doesn't actually show on here. It's more than half the atmosphere is below this level, and at 10 kilometers, I'm guessing it's maybe about 75 or 80% of the atmosphere is below there. So, and it staggers, it gets less and less dense as you go further and further up. All the way up to, even up to 30 kilometers, 40 kilometers, there's still atmosphere there, but it's very diffuse. Okay, so let's go ahead and try to calculate what the pressure is due to the air above us, due to the atmosphere. And we can do that by taking the fact that, we'll say most of the air is, or most of the atmosphere goes up to only 10 kilometers. And what we need to know if we're going to figure out what the pressure is at sea level, say the pressure on a square meter, right? We need to know the force of the atmosphere that's pushing down, and use that 1 square meter to say pressure is that force divided by the area. Okay? So take our 1 square meter and imagine like extending this column, or thinking about looking at this column of air that's 1 square meter around, goes all the way up to the top of the atmosphere. Right? So it's the weight of all of that air in that column that's pushing down on this square meter. So the volume of that would be 1 square meter multiplied by the height of the atmosphere, 10,000 meters. So we get 10,000 cubic meters, and the mass of that, if we use the density of air, turns out to be 10,000 kilograms. And the weight of that air, again, remember if we have mass, here on Earth, we just multiply by the acceleration of gravity, reverse gravitational pull, and that is about 10 meters per second. So 10,000 kilograms multiplied by that 10 meters per second squared gives us 100,000 newtons. So that's the weight, that's the force of all that air pushing down on this square meter. So again, find the pressure on that 1 square meter. We would say the pressure is equal to that force, 100,000 newtons, divided by the area, 1 square meter, So we end up getting 100,000 newtons per square meter, or remember it's 100,000 pascals. In terms of standard units, this turns out to be 15 pounds per square inch. Something like that. And yeah, so I told you that, I think in the last lecture we talked about pressure to begin with, that this is the pressure of the atmosphere. So here I'm just showing you that this is roughly how you can calculate that that's approximately what that pressure is going to be, just knowing the density of the atmosphere essentially. And for sure, just to point out that this is an oversimplification, but it's pretty accurate on average throughout all of the Earth's surface. Right? So 100,000 pascals, that's the pressure. And yeah, so that's essentially also the pressure just anywhere along the surface. Pressure that's exerted on you, exerted all over your body. So remember that the pressure in a gas, just like in a liquid, because they're both fluids, the pressure exerts in all directions. So that 100,000 pascals is pressure that's exerting on all parts of my body right now, right? Except for maybe the bottoms of my feet. Oh, yeah, as long as well. All right, well, now we get to some of the fun part. We're going to see some demonstrations of this pressure, right, of the atmosphere. We call it atmospheric pressure. So one way to see the fact that the atmosphere has this pressure is to take a cup of water and place a flat surface, like you want a nice flat-rimmed cup. There shouldn't be any gaps in it. Place a flat piece of cardstock or just folded paper or anything that's flat that can essentially touch on all the rim of the cup at once. So you fill up the cup, put the piece of paper on there, put whatever your flat surface is on there, you flip it over, and you take away your hand, and the water doesn't fall down. Right? Why is that? Well, the main reason is that what's pushing down on, if you have, say, a piece of paper above the cup, or on the top of the cup, what's pushing down on that paper is the weight of the water in the glass, but what's pushing up is the atmospheric pressure, right? So the weight of the water multiplied by that surface area is not very much, actually, at least in comparison to the pressure of the air pushing on the other side of that. So let's see that next. So he dyed his cup water red. So that's atmospheric pressure pushing up on that piece of paper, and the water, the weight of the water trying to push down on it, and atmospheric pressure wins. All right, so another example of atmospheric pressure and how great it actually is, how much pressure it actually is, or you can see that with these things they call Magdeburg, I think, hemispheres, named after some person, I'm sure, who came up with this idea. But essentially, you can take like a sphere and slice it in half, so you have two hemispheres, and essentially just hook up a valve to one of the hemispheres, and the valve, so you can open it and you can close it, and connect that valve to a pump. So when you put the spheres together, if the valve is open or closed, initially it doesn't really matter, because when you put the spheres together, all you're doing is enclosing the air that's already there. That air is at atmospheric pressure. The air outside of the spheres is atmospheric pressure, so there's no pressure difference between the inside and the outside. You just pull the spheres back apart. You put them together, pull them back apart. However, when you connect the valve to a pump, what that pump is going to do is essentially pull, or yeah, in a way it's going to pull the air, some of the air molecules that are inside of those hemispheres, that sphere, out of them, right? So it's sort of a one-way thing. It's just kind of taking some of that nitrogen and oxygen out of there. And what that does is, since there's now less atoms in there, the pressure inside of that is lowered, and meaning it's lower than atmospheric pressure. So now, inside the sphere, the pressure is lower. Outside, it's still atmospheric pressure. It's still higher than that. And the effect of that is that essentially the pressure of the atmosphere is pushing in on the sides of the hemisphere. And so it wants it to keep it together. And even in this video, we'll see these two, grown men trying to pull these hemispheres apart, and they can't do it. So he's using a hand crank pump to essentially evacuate some of the air out of this hemisphere. So you close the valve off so we don't let air go back inside. So now each of these guys is going to try to pull on the hemisphere, and they're pulling apart. They're trying to force these hemisphere open, but the pressure of the atmosphere is pushing them closed, because the pressure inside is so slow now that the difference in pressure means that overall there's a much greater force pushing the spheres together. Until you open up that valve, you let air back inside, it goes back to atmospheric pressure inside, atmospheric pressure outside, there's no pressure difference. Easy to pull them apart. Alright, so how about one more demonstration for now, having to do with essentially just getting an understanding of how great atmospheric pressure is. And remember that atmospheric pressure is due to the weight of all the air above you, or above whatever object you're talking about. So this was an experiment that Mythbusters did. Mythbusters was a TV show a while ago. They tried to verify or bust all kinds of myths, urban legends, things like that. One of those was essentially that there was a steel tanker, something like a 1/4 inch thick steel, that was cleaned out with hot water, steam, hot water and steam, and the inside. So they were cleaning out the inside, and after they cleaned it out, they got out of the tank, they closed it up, and by closing it off, they didn't allow any air to come inside or outside of the tank. And so what happens is, as the water, that steam in the air that's still inside the tank is hot, it's at a fairly high pressure, but when the tank cools off, the water in the air that's steam now wants to condense and become, the steam that's in the air, it wants to condense and become water. And as it condenses, the gas essentially is contracting, and so it's becoming much smaller as it comes from a gas to a liquid. And what that really does in the end is drop the pressure very significantly. So instead of a gas being everywhere and pushing on everything, you have a liquid that's not really pushing on much anymore. So essentially the pressure drops as the steam condenses into water. And the myth was that it was such a great pressure difference, or drop in pressure, that the difference between the pressure inside and the atmospheric pressure was enough to crush the tanker. Yeah. So I think, as it turned out in this myth, they weren't able to reproduce that, because that difference in pressure just wasn't quite enough to do that. However, like their tradition was that if they couldn't reproduce the myth based on the statement of the myth, then oftentimes they would just go to excess in order to reproduce the results. So what we're seeing here is the tanker, and essentially they've shut off the tanker, closed it off, and connected it to a valve again with a pump. So the pump is pumping air out of that tanker. And what we're seeing here is the pressure gauge, which is showing us our pressure, the pressure in the tanker. And let's just, I guess, give it a watch. So all they're doing is lowering the pressure inside, and it's the pressure from the outside, the atmospheric pressure, that's always pushing down onto this, pushing in all directions. And eventually, the pressure difference becomes so great that it can crush steel. And so the pressure gauge is actually showing that they only had to reduce the pressure inside to about 80,000 pascals, which is still about 80% of atmospheric pressure. But right around there, the tank imploded. All right. So now we need to, we're going to talk about suction, and how suction is not at all what most people think it is. So, for example, when you're drinking through a straw, right? You have a straw, you put it in some liquid, and you generally, colloquially say you're sucking on the straw and you're sucking the liquid up. However, this is not how the world works. There is no such thing as this suction force. Right? There's no sense in that there's some way that inside of you're actually pulling on the liquid in order to get it to come up that straw. What you are doing is lowering the pressure in your mouth and in your lungs, and in that sense, since your lips are around the straw too, they lower the pressure within that straw, and the result of that is that since atmospheric pressure is still pushing on all the rest of the liquid, right? It's still pushing on the liquid wherever your straw's not in there, then the atmospheric pressure is pushing down here, it's pushing that liquid, it's causing pressure in that liquid, and since there's a lower pressure now inside of the straw, that liquid is going to get essentially pushed up by the atmospheric pressure and allowed to rise to that lower pressure area. So there you go. That's how straws work. And we're going to get more into this. So this is related in a way to something you call Boyles Law. And Boyles Law essentially says that the density of a gas is going to increase as you compress that gas, whereas you decrease the volume. Right? So compressing means you're squeezing, you're decreasing this volume. So as the density of the gas increases, right, as you squeeze that gas, the pressure in that gas is also going to increase. So as an example of this image, or this kind of diagram here, if you have a syringe, and that syringe is connected to a tank, so there's air in the syringe, there's air in the tank, and that those things are connected to a pressure gauge. When you push the syringe in, what you're doing is you're compressing that volume of gas. It's going to increase that density of the gas, it's going to increase the pressure in that gas. Right? So what you'll do, if you push the plunger in, you'll see that pressure gauge go up. The opposite is also true. If you decrease the pressure in a gas by, say, expanding the gas, you decrease the density of the gas by opening up the volume and allowing it to expand into a greater volume. So you decrease the pressure, you decrease the density of the gas. And if you, another way of putting that is also that the pressure of a gas is going to decrease as the volume increases. So in the opposite sort of way here, if we already pushed that syringe in, you see the pressure go up. If we were to do the opposite and pull the syringe out, we were to expand the volume of that gas, the density of that gas is going to go down, the pressure is also going to go down. Right? We can see that gauge go down. So this is very much related to how humans and most other mammals, I think, and other number of other organisms, how we respirate, how we breathe. So in terms of breathing, again, it's a sort of a misconception, or maybe not misconception, but just not misnamed in a way, that you might sometimes say that you suck air in, especially if you've been holding your breath for a while, like you've been swimming underwater for a while or something, and you pop out of the water, and you're almost out of breath, and so you kind of like are gasping for air, you're sucking air into your lungs. Right? Remember, there's no sucking force. There's nothing like that. Right? What is happening? Well, we just got to remember that outside in the air is going to be at atmospheric pressure. Right? And our lungs, along with our diaphragm, work. Well, the diaphragm actually does most of the work. It's a muscle that we can contract and expand. And in, say, contracting the diaphragm, right, it pulls down, it expands the volume of the lungs, and because of that, well, along the lines of Boyles Law, when you expand the volume of the lungs, you're lowering the density of the air that's in your lungs, the gas that's in your lungs, you're lowering the pressure of the gas that's in your lungs. Right? And that lower pressure now is nothing, well, essentially, now that there's lower pressure here, the higher pressure of the atmosphere essentially forces more air into your lungs. So you don't suck air in, the atmosphere shoves it into you. Yeah, essentially. And then so when you exhale, right, you sort of expand your diaphragm or relax your diaphragm. What that does is it pushes back up on the lungs, right? It compresses the air, the gas that's in your lungs. That compression leads to a higher pressure, which is now greater than atmospheric pressure. So that now the pressure inside is greater than the pressure outside, and the air is forced out. So in a sense, you kind of spew air out, but you don't suck air in. Yeah. All right, so let's maybe see as example, kind of along these lines, not necessarily along the lines of changing volume, but changing the pressure in some area and watching the pressure of the atmosphere cause something else to move. So in this case, you can do this if you take a hard-boiled egg and a bottle where the opening of the bottle is a little bit too small for the hard-boiled egg. So you can rest the hard-boiled egg in the bottle, but it's not going to fall in. What we can do is, well, what we really want to do is essentially cause the air that's in the bottle underneath the egg to be at a lower pressure, sort of like you contracting your diaphragm and opening up your lungs, expanding your lungs in order for the atmosphere to force air in. Right, so we want to lower the pressure in that bottle, and the way that we can do that, or one way you can do that, is just take a match or light up a piece of paper, and you drop that piece of paper into the bottle and put the hard-boiled egg on top. Right? It's slightly complicated, but what that's going to do is that the flame is going to heat up the air inside. We haven't talked about that much yet, but heating up gas actually increases the pressure of the gas. So when you heat up the air that's inside the bottle, it's at a higher pressure than the air that's outside, and so that air wants to rush outwards. It wants to push out against the atmosphere. And it does that, and you can actually see that. You see the egg start to get pushed up a little bit as the air inside is forced outwards. But once that paper goes out, you're no longer heating up that gas anymore. It cools back down to its normal sort of temperature, and now there's less air in there, it's less dense, it's at a lower pressure than the air outside, than the atmosphere. So now we have a difference in pressure from the outside to the inside. Higher pressure outside is going to push down on the egg, it's going to shove that egg into the bottle. So you got the egg, it's going to light up this piece of paper, drop it in there, and you can watch, you can see the egg sort of bobble around, right, as the air comes out. Ta-da! The egg got sucked in. Kind of cool. So just to say that, like with all these demonstrations, these little videos I show you, all the links are always there, so feel free to pause this video and go check those out in more detail if you ever want. All right, so now that we've talked a little bit about increasing and decreasing density of gas by expanding and contracting it, or a little bit in that demo by heating it up, cooling it down. And from the last lecture on liquids, we talked about buoyancy, and how if you have an object that the average density of that object is less than the density of the liquid that it's in, it's going to be buoyant, it's going to float. The same thing actually applies to gases, right? Because gases and liquids are fluids, they both act in this way, and you can be buoyant in a gas just as you can be buoyant in a liquid. The same reasoning applies, or the same thought process sort of applies, is just that you have to have an object that is has a lower average density than the air around it. So how do you do that? Well, you can do that in a couple of ways. For one, you can just fill up a blimp with a gas that is lighter than air. So you have a helium-filled blimp. Helium is lower density than the atmosphere, and with that much helium, it averages out with the balloon and the little whatever modular holding tank is below, that the average density of that object is less than the density of the air, and that object is buoyant. So similarly, actually, now that I think about it, hot air balloons might be even more similar to that flame in the bottle, in that when you heated up that air in the bottle, it actually wants to push the air out, and the overall leaving the gas that's left in there to be at a lower density, less pressure. All right, so the last sort of overall thing I want to say about gases is another way that the pressure in a gas can decrease. And that is, well, it has to do with Bernoulli's principle, that was put down in detail by this guy Bernoulli, which is that the speed of a fluid is related to the pressure in that fluid. Right? So imagining like wind rushing along, the greater the velocity of the wind, the faster that wind is moving, the lower the pressure is in that wind. Right? So Bernoulli essentially says that in general, that for any fluid, gas or liquid, if the speed of the fluid increases, the amount that it's moving increases, the pressure in that fluid is going to decrease. So this is the same being, applies to all fluids, gases, liquids, plasmas. In a sense, we talked about energy and energy conservation, or the conservation of energy. In a sense, you could understand this as sort of a conservation of energy, where if I imagine just a little, like a chunk of gas or a volume of gas here, all the gases are moving around randomly, but if the gas is not moving in a bulk sense, like it's not like a thing of wind moving along, it's just kind of in this area, then on average there's no net sort of kinetic energy. All of the motion is sort of averaged out, that it's all staying in the same area. Right? However, if you then have all that gas start moving along in one direction, right, then now all that gas, there's a net kinetic energy to that gas. And where did that energy come from? Well, the energy, in a sense, was taken away from the pressure of the gas, right? From the amount that the gas is pushing in all directions. So that's one way of understanding Bernoulli's principle. And yeah, so just some very simple diagrams. If you have still air, then it's going to be at atmospheric pressure, versus if you have wind, it's going to be at a lower pressure than atmospheric pressure. Right? We're not being quantitative here, just atmospheric pressure and lower than atmospheric pressure, or higher than atmospheric pressure. So, and then the faster the wind moves, the lower that pressure is going to get. Cool. So let's see a demonstration of this, right? And you can do this on your own as well. Very easy. We can do this by taking a piece of paper, right? And if I just hold the piece of paper at its ends, then it's going to flop down. Right? Not a trick piece of paper or anything like that. And so Bernoulli's principle says that if I manage to get the air moving faster along the top here, then it's going to be at a lower pressure. Also meaning that the air below it's going to be at a higher pressure, and that difference in pressure amounts to a force overall that's going to push this paper up. Let's see. That one starts so great. There you go. All right, so you can do that on your own too. Ooh. Yikes. Well, I did it at least once. I don't know. Oh, there you go. Right? A little lightheaded there. Yeah. So there you go. The movement of the air, that bulk sort of movement means there's lower pressure in the air here, higher pressure in the air below it. Overall, there's a force pushing that piece of paper up. It's a nice, easy one to do on your own. All right, so how about a little check for yourself, having to do with Bernoulli's principle and difference in pressure when you have a lot of wind movement. So, you know, if you're thinking about being on the ocean somewhere and you have these little bit of waves sort of building, and then you also have a strong wind blowing by. That wind, again, that movement of air is going to cause the pressure to be lower in some areas than it is in other areas, right? So where in this picture would you say that the pressure is lower than atmospheric pressure? All right, well, it might be a little bit tricky, but essentially as the wind moves across these sort of ripples, little waves, right, the wind isn't able to dip down as much into these sort of valleys. So the air is not going to move quite as much inside of those little dips. So largely it's going to still be at atmospheric pressure. Whereas the wind moving along the top of these waves, right, it's moving quickly along the top, so we're actually lowering the pressure along the tops of these waves, along the crests of these waves. And this is the one way, or the main sort of way of understanding why on a windy day, waves in general are going to be much bigger than they would on a calm day. Okay? So on a calm day, there's still going to be waves, but when there is wind and high winds, this effect of Bernoulli's principle means that the bottoms, the crests, troughs of the waves are still going to be sort of pushed down atmospheric pressure, but the tops of them are not pushed down as much because the pressure is lower than it would be on a calm day. So that lower pressure means the waves and crests can get higher and higher. So another consequence of this principle that moving air is lower pressure is, well, the roofs of buildings can be blown off, pulled off, or pushed off more like it, in very high winds. So this diagram kind of shows this happening, where if you have very high winds moving along, then that means there's a much lower pressure above the roof than there is inside of the house, because the air is still still, it's still at atmospheric pressure. So essentially we now have a much larger pressure pushing from below than we do pushing down from above. So again, the net result is that there's this force that's pushing up on the roof. And if that wind gets high enough, then that pressure is going to be very, very low. Overall, that net force is going to be very great and can lift the roof off. And yeah, the image happened to parts of this the Superdome. Cool. So we could also use this this principle, this fact, that moving air is a lower pressure than still air in order to levitate an object. And again, it's going to take my breath to do this, so hopefully it's better. So all I need for this is some kind of funnel and a ping pong ball. It's pretty nice, right? So put the ping pong ball in, flip the funnel over, it falls out, right? Same amount of pressure above and below the ping pong ball. So the only thing, the net effect on this ping pong ball is just the force of gravity pushing it down, right? However, if I blow very strongly into this funnel while the ping pong ball is sitting in it, then what that's going to do is lower the pressure of the air that's above the ping pong ball. The pressure from below is still going to be about atmospheric pressure, so it's going to be, the net effect is that there's going to be a force pushing that ping pong ball upward. And if I can blow hard enough, it's that effect of the force from the difference in pressure is enough to counter the gravitational force. So let's see. Oh, that kind of worked. Okay. For a second at least, kind of difficult. There you go. All right. So again, another example of Bernoulli's principle. All right, and the final thing that's interesting to mention about or use of this effect is in causing lift and generating lift for aircrafts. So as it turns out, the way that aircrafts generate lift, there's there's a couple of different ways, but in general, the way that an aircraft is going to be able to get lift is due to the shape of the wings. So the shape of the wings are in this particular shape, which we call an airfoil, and it's named as such because it has this particular effect or this particular shape that essentially causes the air to move over the bottom and the top of that airfoil in different ways. So the shape of a wing is such that it causes when the wing is pushing through the air, pushing through the atmosphere, the air along the top of the wing is in a sense forced to move faster than the air that's moving below the wing, right? So the air moving below the wing is still sort of moving at a certain rate, but this air on top is going faster than that air, right? So again, the net effect is that air moving faster on the top means it's a lower pressure along the top than it is along the bottom, and the net effect of that is that there's a force upward. The difference in pressure amounts results in a force pushing upwards, and we call it the lift force. Yeah, this is at least one way of understanding how airplanes work. Airplanes, it's interesting if you read into them more. The effect of an airfoil is quite complicated in some sense, right? But in a simple sense, Bernoulli's principle explains it in that there's just a difference in the speed of air moving above and below the wing. All right, so just wrap this lecture up by, as I mentioned, we'll tell you a little bit about plasma. So plasma is the fourth sort of state of matter. It is essentially, the easiest way to understand it is essentially it's a gas that has been ionized. So if you recall from the lecture on the about atoms, the atomic nature of matter in the universe, that ionized means the atoms have an electrical charge, meaning they have either an excess or a deficit of electrons. Right? If you have extra electrons, that's more negative charge, then you're more negatively charged. If you have a deficit of electrons, then you have less negative charge, and that ion is positively charged. And a gas or a Plasma is basically a positively ionized gas, meaning it's a gas where the atoms have lost some amount of their electrons. So what ends up happening, or what you end up with in the end, is when you have atoms that have kind of kicked off a bunch of their electrons, then we essentially have this new sort of gas where the thing that's making up the gas is now basically usually like the nuclei that have kicked off all of their electrons, which are positively charged. And then you have the electrons that are also still there, but they're kind of free. They're in their own sort of gas state, right? So we have these positive nuclei, we have these negative electrons, right? And it's a gas, sort of a mixture of those things. And being that it is electrically charged overall, each of these things is their own little electrical charge, and they're not close enough together in the atoms to really neutralize any of that overall charge. Plasmas will conduct electricity. And some examples of different plasmas, well, we have these little like plasma lamps, which are kind of fun to play with, but essentially inside that lamp there's a gas, and the middle of the inside of that, the ball in the middle is something that can put off electrical energy in order to give energy to the atoms in the gas. And by giving energy, is one way of essentially kicking electrons off of the atoms of that gas. Right? And when you go ahead and put your hand on the sphere, the outside of the sphere, then that electrical energy has a path to go to, has a place to go to, so it wants to go towards your hand, which is why you end up ionizing the gas in between that center sphere and where you touch the outside of it, and that ionized gases are plasma. The sun is very largely made out of plasma. It's so energetic that all the atoms in the sun, pretty much all the atoms in the sun, are not in a state where there's electrons and protons and neutrons and all kind of together as atoms. They all have so much energy that the electrons are all separate, essentially, from all the nuclei. Right? And there you go. That's a plasma. Another example of a plasma is lightning. So, lightning is essentially a phenomenon, I think I'll mention this later on too, but where there's so much difference in energy between, electrical energy between the clouds and the surface of the earth, that all of the air in between there, maybe it's going to be difficult to explain right now. But essentially, a bunch of electrons from, I believe the cloud, want to jump down to the Earth in order to sort of neutralize the difference in energy between the cloud and the Earth. And that movement of electrons is, in a way, creates a plasma that we see as this lightning bolt, right? Also, arc welders, if you ever see an arc, that's also a form of plasma. So, funnily enough, plasma it's not a very common state. It's the least common state of matter on Earth. But if you think about it, like I said, the sun's made of plasma, and the vast majority of the sort of the stuff that makes up the universe there's tons and tons of stars, right? So stars make up a large majority of the stuff of the universe, which means that plasma is actually the most abundant state of matter in the universe. Probably followed by gas after that. So some other examples of plasmas would be fluorescent light bulbs. So in fluorescent lights, you essentially have a gas inside of these tubes, and you essentially dump a bunch of electrical energy into those tubes so that it knocks the electrons off of the atoms in the tube, and you have a plasma, and that plasma can now conduct this sort of path for electricity inside of the tubes. Another example are the auroras. So the aurora borealis in the northern hemisphere, the aurora australis in the southern hemisphere, where the auroras are created by sort of junk stuff kicked off by the sun that gets directed to the poles of the Earth via our magnetic fields, which we'll talk about some more later. But essentially that charged stuff, it gets shot off from the sun, it gets directed towards our atmosphere, and as it moves into our atmosphere, it crashes into the atmosphere, the atoms that make up the atmosphere, knocking off all of these electrons from all the different atoms, and creating a plasma briefly, and as that plasma sort of recombines, it ends up giving off light, which we see as these auroras. And so the last thing I'll show you is a little example of plasmas. So in this video, each of these tubes are just essentially enclosed tubes, and they each have gases inside them: hydrogen, helium, neon, argon, krypton, xenon, and nitrogen. And all that the person's going to do is they're going to bring this, I think it might be a Tesla coil or something, but essentially an object that can give off a bunch of electrical energy, and that electrical energy is very intense close to the source of that, but it fades off pretty quickly as you get away, as an inverse square in fact. But so that means that when you bring this source of electrical energy close to any of these one tubes, it's dumping a bunch of electrical energy into that tube. The tube is, the atoms in that tube are separating into nuclei and electrons, and we have a plasma. And again, when that plasma sort of, just like the auroras, that plasma recombines, then it gives off photons, and actually gives off photons in a particular wavelength that's characteristic of each of these gases. So what we're going to see is essentially he's going to bring this Tesla coil, I think it's Tesla coil, by each one of these tubes, and as he brings them closer, you actually see the plasmas being formed and sort of recombining into gases. So he has all the, looks like the atomic weights on there, the atomic number at the top, number of protons, the atomic weights at the bottom. Right, and they're not connected to anything. And here we have a nice coil that can give off a bunch of electrical energy. And there you go, he turns it on, and while they're close to any of these tubes, it's giving off enough energy in that area to ionize and create a plasma in these tubes. And when that plasma recombines, we get our visible photons coming out. So I don't expect you to understand or get too much about plasma. I didn't talk about plasma too much, but partly because, you know, on a day-to-day sense, you're probably not going to deal much with plasma, right? We deal with solids, liquids, gases. That's mostly what we deal with. So I spent most of the time talking about gases, and in a large part talking about atmosphere. The atmosphere and atmospheric pressure, because it is extremely important and practical. Yeah, but that's all I got for this lecture. And next time I think we're going to talk about temperature. So have a good one. I'll see you next time.